Why has it been 13.8 billion years since the universe began, and yet we still don't know how it all started? Humanity has walked on the moon, explored the deepest corners of science, and uncovered countless mysteries. Yet we still struggle to understand where we came from. Isn't that absurd? As the most advanced species on Earth, we seem to have immense intelligence, but we are stumped by one of the most basic questions of all. Finding the right answer to this question is not simple. Over the next 46 minutes, I will take you on a journey, using everything you've learned in physics and astronomy, to explore the universe's origins. We'll travel across 13.8 billion years of cosmic history to finally answer this question, and along the way, we will clear up all your confusion about space exploration. By the end of this, you'll see the universe in a completely different light. Let's begin with the strange nature of the universe itself. It's odd, isn't it? We're so used to the twinkling stars and the sprawling galaxies that we forget, if you traveled back to 13.8 billion years ago, you wouldn't even see a speck of dust in the sky, because the universe didn't even exist. That's right, there were no stars, galaxies, or even space itself, just pure, absolute nothingness. But what's even more baffling is what happened next. In an instant, imagine that, an unimaginable moment, this emptiness underwent a dramatic transformation. With a single, explosive bang, everything we know and see in the universe today came into being. Yes, you read that correctly, the entire universe, in a split second, sprang into existence from nothing. It seems too extreme, but it's not a story. This is exactly how our universe came to be, spontaneously, from pure nothingness to everything we see today. Now, we may have some impressive scientific theories, but when it comes to the ultimate question of the universe's origin, even scientists remain utterly confused. Why did the universe suddenly appear out of nowhere? What made it emerge from complete emptiness? Even stranger, where did this emptiness come from? To help explain this, the world-renowned physicist Stephen Hawking proposed a bold idea. He suggested that before the universe existed, there was no such thing as time or space. This means that asking what the universe was like before it began is as nonsensical as asking what's north of the North Pole. There simply wasn't anything. For Hawking, the birth of the universe was not just the beginning of space, it was also the beginning of time itself. It might sound fantastical, but surprisingly, scientists accepted this idea. Because when you trace the universe's history back, you encounter a time so extreme that it's almost impossible to comprehend, something scientists call the Planck era. In the Planck era, the universe was compressed into an unimaginably tiny space. Its temperature was unbearably high, and its density was beyond description. During this period, the universe didn't follow any of the familiar physical laws we know today. It was a chaotic, incomprehensible mess, a giant stew where space, time, and energy were all jumbled together. And from this chaotic state, how did we end up with the universe we see today? This is where the theory of cosmic inflation comes in. Scientists hypothesize that, just moments after the universe's birth, space expanded at an incredible rate, inflating billions of times faster than light. But what triggered this explosion of expansion? And what dramatic changes did this chaotic explosion bring to the universe? As mind-boggling as it sounds, scientists believe that our universe is just one of many in a multiverse. That inflationary event may not have been a one-time occurrence. In fact, the idea of the multiverse theory suggests that the universe you and I live in could be just one bubble among countless others. Each bubble would follow its own set of physical laws, leading to entirely different universes. And then there's another theory, even more daring, the Big Bounce. Instead of a singular beginning, the universe might go through cycles of expansion and contraction, with each Big Bang being just the start of a new cycle. The universe we know could simply be the latest iteration in an ongoing cycle. Let's explore how the universe gradually settled into the organized system we observe today. After the Big Bang, the universe was in a state of extreme chaos, where all four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were all tangled together. But as the universe expanded and cooled, these forces gradually began to separate. First, the electromagnetic, strong, and weak nuclear forces unified into a single superforce known as the electroweak force. This happened when the universe was incredibly small and hot. But gravity, well, gravity didn't play along. Even scientists today still don't fully understand why it didn't fit in with the other forces. At this point, an incredible change began to take place. As the universe cooled further, the electroweak force split into the electromagnetic force and the weak nuclear force, which continued to stay intertwined for a while. Eventually, the forces all separated and began to operate independently. forming the familiar forces we know today. But the question is, why did the universe divide like this in the first place? It was once perfectly symmetrical, perfectly balanced. What caused it to break apart and develop into the diverse, dynamic universe we know? This process is called spontaneous symmetry breaking. Scientists believe that the early universe was perfectly symmetrical, but as the temperature dropped, something changed, and this symmetry broke. That tiny imperfection led to the changes that set the universe on the course to its current state of complexity. The key to this transformation lies in a mysterious field, the Higgs field. In the 1960s, British physicist Peter Higgs proposed a bold idea: there exists a field throughout the universe that imparts mass to particles. Just like how you slow down when walking through a crowded street, particles gain mass when they interact with this field. The particle that carries this field's effect is called the Higgs boson. In 2012, the Large Hadron Collider discovered this elusive particle, confirming Higgs's theory. This discovery explained why particles have mass. It's due to their interaction with the Higgs field. Thanks to the Higgs field, the universe went from perfect symmetry to diversity. Particles gained mass. Electrons became lighter, quarks became heavier, and atomic nuclei became stable, leading to the rich variety of matter we see today. But even as the universe gained mass and complexity, new mysteries arose. The universe is full of matter, but where did all the antimatter go? Antimatter and matter should have existed in equal amounts when the universe began. So why is the universe now almost entirely composed of matter? The concept of antimatter might sound like something out of science fiction, but it's very real. In 1928, physicist Paul Dirac created an equation that combined quantum mechanics with relativity. To his surprise, the equation predicted the existence of particles that were identical to electrons but with opposite charges, positrons, or anti-electrons. These particles were later discovered in cosmic rays, confirming Dirac's prediction and the existence of antimatter. When matter and antimatter meet, they annihilate each other, releasing immense energy. The mystery, though, is why there's so much more matter than antimatter in the universe. In the early universe, matter and antimatter should have existed in equal amounts. But scientists discovered that the weak nuclear force, the force responsible for radioactive decay, was not entirely fair when interacting with matter and antimatter. It produced slightly more matter than antimatter, and this small bias allowed matter to dominate. Without this imbalance, we wouldn't be here today. Even though antimatter is rare in the universe, it does appear. For example, when high-energy particles emitted by the Sun collide with Earth's atmosphere, they create small amounts of antimatter. There are also regions near supermassive black holes where antimatter can form. Interestingly, even in everyday objects like bananas, there are small amounts of radioactive elements that emit positrons during their decay. But don't worry, the antimatter in bananas is far too small to pose any threat to us. Still, the fact that antimatter is so rare in the universe may actually be our cosmic good fortune. If there had been an equal amount of matter and antimatter, they would have annihilated each other, and the universe as we know it would never have existed. But now, let's take a step further back to another fundamental question. How did the elements we rely on for life, carbon, oxygen, nitrogen, come into being? In the early universe, there were no elements. There was only hydrogen and a little bit of helium. So how did these elements form? About 3 minutes after the Big Bang, the universe was hot enough and dense enough for nuclear fusion to take place. Initially, the universe was just a huge nuclear furnace, with particles colliding and fusing to form hydrogen, helium, and trace amounts of lithium and beryllium. But this fusion didn't stop there. The process continued for about 20 minutes, and in that short time, the universe produced a significant amount of helium, about 25% of all the matter in the universe. The rest remained as hydrogen, with tiny traces of other elements. So, how did these simple elements evolve into the complex elements we know today? The answer lies in the first stars that formed a few 100 million years after the Big Bang. These first stars were massive, much larger than our Sun, and burned through their fuel incredibly quickly. After only a few million years, they exploded in supernovae, creating heavier elements like carbon, oxygen, silicon, and iron. These elements were then scattered throughout the universe, enriching the interstellar medium and contributing to the formation of new stars. Without these first-generation stars sacrificing themselves in supernova explosions, the elements necessary for life, like carbon, would never have formed. These explosions pushed the process of galaxy formation forward, compressing gas clouds to create new stars. The heavier elements formed in these stars then became the building blocks for planets like Earth. This brings us to another fascinating part of the universe's evolution, the role of dark matter. Dark matter is one of the most mysterious forces in the universe. It doesn't emit light, nor does it interact with electromagnetic forces, which is why we can't see it. Yet, dark matter accounts for more than 85% of the mass of the universe. The matter we can see only makes up a small fraction of the total mass. How does dark matter work? Dark matter is thought to form an invisible scaffold behind every galaxy, helping to hold it together. Imagine it as a kind of cosmic glue, pulling gas clouds and stars into orderly structures, leading to the formation of galaxies. Our own galaxy, the Milky Way, is no exception. It has between 100 billion and 400 billion stars, most of which are second- or third-generation stars that have inherited heavier elements from the first-generation stars. In recent years, we've made a remarkable breakthrough in observing the universe's early stages. The James Webb Space Telescope, launched in 2022, has provided humanity with the most advanced tools yet to observe the early universe. This high-tech telescope directly observed galaxies that formed shortly after the Big Bang. The results? They shocked scientists. According to previous theories, the first galaxies should have been somewhat rudimentary in structure, not very mature. But what the JWST revealed were galaxies far more complex and organized than anyone had imagined. These galaxies had more stars, better developed structures, and were far more mature than the model suggested. This discovery forced astronomers to rethink their theories. Did galaxies form faster and more efficiently than we thought? Could dark matter have played an even larger role than previously considered in the formation of these early structures? Was our understanding of early star lifespans and masses inaccurate? These new findings remind us of the true nature of scientific exploration. Every time we feel like we've got the universe figured out, new mysteries pop up, offering new clues, new puzzles to solve. This is what makes exploring the universe so fascinating. Now, let's return to one of the biggest questions in this journey. How did planets like Earth, capable of supporting life, come into being? And how did the essential elements for life, like carbon, oxygen, and nitrogen, make their way into the universe? It turns out, the answers are tied to the formation of stars and the creation of heavier elements in their cores. As the first stars were born, they started to fuse lighter elements like hydrogen and helium, creating heavier elements like carbon, oxygen, and iron. These stars then exploded in supernovae, scattering these elements across the cosmos. These elements became the building blocks for new generations of stars, planets, and eventually, life itself. But the real mystery lies in how the elements we rely on for life made it to Earth. After the first stars produced the heavy elements, these elements were scattered into space. Over time, they formed clouds of gas and dust that eventually collapsed to form new stars and planets. The process of stellar evolution continued, and eventually, our solar system formed. But Earth, like other planets, needed more than just heavy elements to support life. It needed the right conditions. And the perfect conditions for life to arise? They were a result of Earth's unique position in the universe. So, how did Earth's unique conditions come to be? The answer lies in the fine balance of factors like distance from the Sun, the presence of liquid water, and the ability to maintain a stable atmosphere, conditions that, just like our own planet, are rare in the vast expanse of space. Life, as we know it, could only form because Earth had the right combination of these factors at the right time. But the question still remains what is the origin of life itself? The basic building blocks for life, carbon, hydrogen, oxygen, were scattered throughout the universe. But how did these simple molecules come together to form complex life? And why did this process happen on Earth and not elsewhere? Scientists have long speculated about the seed of life, the idea that the fundamental ingredients for life might not have originated on Earth, but were carried to our planet from space. This theory, known as panspermia**, suggests that life's building blocks might have come from comets, asteroids, or interstellar dust, essentially, from the very fabric of the cosmos itself. This hypothesis is supported by some startling discoveries**. In 1969, scientists detected formaldehyde molecules, which are made of carbon, hydrogen, and oxygen, in interstellar clouds. Since then, more complex organic molecules, such as amino acids and other prebiotic compounds, have been found in deep space. In fact, meteorites that have landed on Earth, like the famous Murchison meteorite in Australia, have been found to contain complex organic molecules and even nucleotides, key components of DNA and RNA. This has led to the suggestion that life's building blocks might have been seeded across the universe, potentially arriving on Earth via meteorite impacts. Asterisk asterisk, what does this mean for the origin of life on Earth? Asterisk asterisk. It implies that life might not have started here at all. Instead, it could have been seeded from elsewhere in the universe, carried by space rocks and meteorites, and then evolved into complex life under Earth-specific conditions. This theory is gaining traction, with many scientists now considering the idea that life in the universe might be more common than previously thought, simply because the building blocks for life are ubiquitous in space. But asterisk asterisk, life's origins asterisk asterisk still remain one of the greatest mysteries of all. Even though we understand more about the ingredients for life, how exactly these ingredients came together to form life, especially complex, multicellular organisms, is still unclear. Asterisk asterisk, let's consider another big question asterisk asterisk. How did Earth's life evolve from simple organic molecules into the complex forms of life we see today? In Earth's early years, about 4.5 billion years ago, the planet was a chaotic furnace of volcanic activity, flowing lava, and intense ultraviolet radiation. The environment was harsh, making it seem impossible for life to form. However, this extreme environment actually provided the perfect conditions for life to emerge. Scientists theorize that, in the presence of these extreme conditions, Earth's surface began to form oceans of liquid water, an essential ingredient for life. These oceans, filled with organic molecules from space, created the perfect chemical lab for life to begin its evolutionary process. In the 1950s, scientist Stanley Miller famously simulated these early Earth conditions in a lab and successfully created amino acids in just 1 week. This groundbreaking experiment demonstrated that, under the right conditions, life's building blocks could form naturally. Asterisk asterisk, but the process of turning simple molecules into life wasn't instant. Asterisk asterisk. Life evolved over billions of years, from simple molecules into complex, self-replicating systems. While the exact details of this transition remain elusive, it is clear that the universe provided Earth with everything it needed to spark life. From the stars, to the molecules in space, to the extreme conditions on Earth, everything came together to make life possible. Asterisk asterisk, now, let's explore another fascinating question asterisk asterisk. How did life go from simple molecules to the complex forms we know today? About 4.5 billion years ago, Earth was a chaotic place, a boiling cauldron of volcanic eruptions, flowing lava, and intense ultraviolet radiation. This environment seemed far too hostile for life to emerge. But in an ironic twist, these very extreme conditions provided the perfect setting for life to begin. Scientists theorize that, amidst these harsh conditions, Earth began to accumulate vast oceans of liquid water, one of life's most essential ingredients. These oceans were enriched with organic molecules that arrived from space, forming a chemical soup perfect for the formation of life. It was in these primeval oceans, perhaps near volcanic vents or lightning storms, that the very first building blocks of life began to assemble. In the 1950s, scientist Stanley Miller famously conducted an experiment where he simulated early Earth conditions and successfully created amino acids within a week. This groundbreaking experiment showed that the ingredients for life could form naturally in the right environment. Asterisk asterisk, but turning these simple organic molecules into actual life wasn't instant. Asterisk asterisk. The process took billions of years, from basic molecules into complex, self-replicating systems. The evolution of life wasn't a sudden event, it was a gradual and continuous process that eventually led to the diversity of organisms we have today. While scientists haven't figured out all the exact steps of this journey, it's clear that the universe provided the necessary building blocks for life, and Earth's unique conditions allowed life to take hold. From the stardust of exploded stars to the organic molecules in deep space, everything came together to make life possible on Earth. Asterisk asterisk, so, what does this mean for the broader universe? Asterisk asterisk. The discovery of organic molecules in space suggests that life, or at least the basic ingredients for life, might not be as rare as we once thought. If life's building blocks are common throughout the universe, it raises the possibility that life exists elsewhere in the cosmos. After all, the universe is vast, with billions of galaxies, stars, and planets. Could there be other Earth-like worlds out there, capable of supporting life? Asterisk asterisk, let's take it even further. What about the possibility of intelligent life beyond Earth? Asterisk asterisk. The Fermi paradox, named after the famous physicist Enrico Fermi, poses a curious question. If there are so many potentially habitable planets in the universe, why haven't we encountered any extraterrestrial civilizations? With so many stars and planets in the galaxy, it seems almost certain that intelligent life should exist somewhere. So why haven't we found any signs of it? Some scientists believe that the solution to the Fermi paradox lies in the idea of the Great Filter, a theoretical obstacle that prevents life from progressing beyond a certain point. This filter could exist at any stage of a civilization's development, from the emergence of life itself to the rise of advanced technological societies. Perhaps most civilizations don't make it past the filter, which could explain why we haven't encountered any others. Yet? Others believe that intelligent civilizations might exist, but they're simply too far away for us to detect. With the vast distances between stars, it's possible that extraterrestrial civilizations are out there, but they're so far away that we can't communicate with them, at least not with our current technology. And what if we're not alone? The idea of multiple universes or this multiverse theory takes things even further. What if our universe is just one of many, each with its own set of physical laws and conditions? In this scenario, other universes could exist with completely different forms of life, or perhaps entirely different versions of what we consider life. Some theorists argue that the multiverse could explain the fine-tuning of our own universe, the idea that the physical constants and laws of nature seem to be perfectly set for the existence of life. If there are countless universes with varying conditions, perhaps we just happen to live in one that is suitable for life. This brings us back to one of the most profound questions of all. What is the purpose of all this? What's the ultimate meaning of life and the universe? Is there a reason for our existence, or are we just a product of random cosmic events? These questions have puzzled humanity for millennia. Some people turn to religion, others to science, and some remain agnostic, unsure of whether we'll ever know the answer. But perhaps the real value of exploring the universe lies not in finding definitive answers but in the quest itself, the search for knowledge, the thrill of discovery, and the humbling realization that we are part of something far greater than ourselves. In the end, the universe may not have a clear, ultimate purpose that we can easily understand. But by continuing to explore, question, and reflect, we unlock new mysteries, redefine our place in the cosmos, and push the boundaries of human curiosity. In many ways, the pursuit of knowledge is the true essence of our existence. As we continue to ask deeper and more profound questions, we propel humanity forward, ever closer to understanding not just the universe, but our own existence. We are humble in the face of the cosmos, but it is precisely because of this humility that we have the potential to continue exploring, learning, and uncovering the most profound mysteries of all. The universe is a riddle, a challenge, and a source of endless inspiration for us all. We live in a universe filled with mysteries, some we may never fully understand, and others we're only just beginning to comprehend. But the journey of exploration, discovery, and reflection is what truly defines us. We are living in this vast, enigmatic universe, and our mission is to keep searching for meaning and answers. But what happens when we look beyond Earth? As we explore deeper into the cosmos, another key question emerges: how did the elements we rely on for life, such as carbon, oxygen, nitrogen, and iron, form in the first place? When the universe first began, there were no complex elements, just hydrogen and helium. So, how did everything we see today come to be? The answer lies in the first stars. A few 100 million years after the Big Bang, the universe was cool enough for the first stars to form. These stars were massive, many times the size of our sun. They burned through their fuel at incredible rates, and in just a few million years, they exploded in supernovae. These cataclysmic explosions scattered heavy elements like carbon, oxygen, and iron throughout space. This was the beginning of the process that would eventually lead to the formation of planets, like Earth. As the universe continued to expand, gravity caused clouds of gas and dust to condense and form new stars. The elements produced in the deaths of the first stars mixed with these new clouds, leading to the birth of new generations of stars, and eventually, planets. And here's the truly extraordinary part. The elements needed for life, carbon, oxygen, nitrogen, didn't just form on Earth. They were scattered across the universe, traveling through space, and ultimately finding their way into planets like ours. The basic ingredients for life were delivered by the stars themselves. Without the violent explosions of these first-generation stars, life as we know it wouldn't have been possible. The universe itself provided the necessary ingredients, and Earth, with its unique conditions, was the perfect stage for life to take hold. But it's not just the formation of elements that we need to understand, it's how these elements came together to form life. This is where the question of life's origins becomes even more intriguing. Earth's unique conditions, its distance from the sun, the presence of liquid water, and a stable atmosphere were crucial in enabling life to develop. But where did the building blocks of life come from? This is where the theory of panspermia comes into play. Panspermia suggests that life's building blocks may not have originated on Earth at all. Instead, they may have been carried to Earth from space, perhaps by comets or asteroids, and then evolved into the complex life we see today. This theory implies that life may be far more widespread in the universe than we previously thought. So, could life exist elsewhere in the universe? Given the vast number of planets and stars in the universe, it seems likely that other life forms could exist. Perhaps they're very different from us, or perhaps they're based on similar principles. But the true question remains, what defines life? What makes a planet capable of supporting life? And here's another question. If life is so widespread, why haven't we found any signs of intelligent life yet? This is known as the Fermi paradox. With so many stars and planets in the universe, the odds of intelligent life existing somewhere seem high. So why haven't we encountered any? Some scientists believe the solution to this paradox lies in the idea of the great filter a hypothetical obstacle that prevents life from advancing beyond a certain point. This filter could exist at any stage of a civilization's development. Perhaps, like us, other civilizations might face a point where they fail to progress, and as a result, we never hear from them. Alternatively, it's possible that intelligent civilizations do exist, but they're simply too far away. The universe is vast, and the distances between stars and galaxies are incomprehensibly large. Even if other civilizations exist, they might be so distant that we can't detect their presence with current technology. Or perhaps we're just one tiny part of a much larger, more complex reality. The multiverse theory suggests that our universe might not be the only one. There may be countless other universes, each with its own set of physical laws. This theory, though speculative, could offer an answer to the fine-tuning of the universe, why the conditions for life seem to be so perfectly set. If there are countless universes, each with different conditions, perhaps we just happen to live in one that is suitable for life. But as mind-bending as this all seems, the universe has a way of challenging us with even bigger questions. What is the true purpose of all this? What is the ultimate meaning of life? Why are we here, and what role do we play in the grand cosmic picture? These questions have puzzled humanity for centuries, and likely will for centuries more. Some look to religion, others to science, and some remain agnostic, unsure if we will ever find the answers. Yet, perhaps the pursuit of knowledge and understanding is the true essence of our existence. The search itself, the desire to discover, to learn, and to grow, may be the very reason we are here. After all, the universe is not just a set of problems to solve. It's a vast, ever-evolving mystery that offers us an opportunity to think, to explore, and to stretch the limits of our imagination. Every new discovery opens doors to new questions, pushing us to dig deeper into the unknown. The true beauty of exploring the universe may not lie in finding the answers, but in the process itself, the questions that propel us forward, the discoveries that change our perspective, and the endless curiosity that keeps us going. And perhaps, in the end, that's the most profound discovery of all. We, as humans, are just a small part of a much larger cosmic story, a story we're still in the process of unraveling. As we continue to explore, ask questions, and seek answers, we become more connected to the universe around us. Each answer we uncover leads to more questions, and each question opens the door to new horizons. In the face of the cosmos, we remain humble, but also curious. It's this balance, humility and curiosity, that drives us to keep exploring, to keep asking, and to keep discovering. After all, we live in a universe that is full of mysteries that are just waiting for us to uncover. We live in a universe full of mysteries. And it is these mysteries that inspire us to keep exploring, asking questions, and discovering. Every answer we uncover leads to more questions, and each question opens the door to new horizons. In the end, perhaps this is the most profound discovery of all. As humans, we are just a small part of a much larger cosmic story, a story we are still in the process of unraveling. As we continue to explore, ask questions, and seek answers, we become more connected to the universe around us. Each answer we uncover leads to more questions, and each question opens the door to new horizons.